Hello and welcome everyone. Good morning. Welcome to reInvent. My name is Mark. I'm an engineer. I work on DSQL and I'm joined by my colleague, Raluca. She's a database engineer. She works on DSQL with me. And this is a code talk. This is a developer's perspective. We're going to be building a very simple application in DSQL this morning using Lambda. And I'm going to show you how to connect to DSQL, how to use the CDK to manage your infrastructure declaratively. We're going to be writing some banking application, just very simple application. It turns out I owe Raluca money, so I need to settle my debts with her. and we're going to be showing you how to scale that application up, how to deal with concurrency, what happens when there's conflicts in the application. This is really meant to be a bit of a baking show, and so there are going to be moments where the pie is in the oven. We're going to be waiting for it. So feel free to ask us questions. Yeah, let's get into it.
All right. I'm going to take over Mark's computer.
Okay.
It's part of his paying his debts to me.
So quick show of hands. Who here has used DSQL? Okay, that's about what I expected. So DSQL was announced at reInvent this time last year in preview, almost exactly a year ago, and became generally available earlier this year. We're about 6 months old now. So what is DSQL? DSQL is a distributed implementation of Postgres. And so for the longest time, customers have been asking us, hey, we really like relational databases. We like being able to do joins, manage our schema, run complex queries. But we also like systems like DynamoDB, where there's no single point of failure, where the system scales horizontally. And we also like services like Lambda, where I don't have to think about infrastructure or scaling or patching or security or anything like that. So these three things, I want them in one package, and that's what we set out to do, and that's what DSQL is. DSQL has 4 pillars. You can find these on our website: virtually unlimited scale, high availability, no infrastructure management, and ease of use. Okay, let's hop on over to the DSQL console and create a cluster. This is going to go by really fast. I challenge you all to count to 10, 5, 4, 3, 2, 1.
I was late.
I can't count to 10. There we go. Okay, great. So that's what it looks like to create a DSQL cluster. It's pretty fast. We've just rolled out fast cluster creation about 2 weeks ago. Let's do that in slow-mo. So Raluca, take us back on over. You'll notice that there's actually 2 options there in the drop-down. There's single region or multi-region. For today's talk, we're going to be focusing on single region clusters. There is no scroll bar on the screen. This is something that I'm just like super excited about because I've made a ton of databases in my career. And every time I make one, I find it just like really awful because I have to make all these decisions ahead of time. It's really hard to decide what instance type do I want, how many replicas, what subnet should I be in, what security. There's just this endless list of choices, and they all really matter. And so which one of those is going to be the one that causes an outage and makes me wake up in the middle of the night? And in DSQL, you don't have to worry about any of that stuff. You can tag your cluster. If you want to change the tags later, go ahead and do that. Clusters are always encrypted by default. If you want to change to a different key, you can do that here. If you want to change your mind later and move to a different key, you can do that later. You can toggle deletion protection, and we've recently rolled out some advanced security options for some of our customers. But that's really all there is to it. Let's connect to DSQL cluster, Raluca.
Right on. Let's choose this one. Have you done anything with it?
Nope, not yet.
Okay.
Okay, so we have 2 ways to connect to the DSQL cluster. This is the query editor. We actually only shipped this about 2 weeks ago, and this is just a Postgres editor running in the web browser, right? What's really cool about this editor is that your browser is connecting to DSQL directly. DSQL supports WebSockets, and so your browser is just connecting over and speaking the Postgres protocol right there. We also have a Cloud Shell integration, so every every page in the AWS console has a little shell at the bottom left. I don't know if you've all seen that. But you can also go to any DSQL cluster and click Connect with Cloud Shell. It will just fill in the prompt with everything that's needed to connect. Okay, so that's getting started. We're going to swap over here, and we're going to start to build an application.
All right.
Okay. So before we do that, I want to orientate you. So I've built a little starter kit for this code talk. It's on GitHub if you would like to check it out. We've got a link. We can share it with you after the talk. And there's a little starter kit, and it's got two key folders. The first one is the CDK folder, and the second one is the Lambda folder. I'm actually going to start with the Lambda one because it's really simple. Here we have a function. Actually, quick show of hands. Who here has built a Lambda function before? Okay, almost all of you, great. Okay, so I won't go into too much detail here. We have a request handler. This request handler is taking an event. The input is going to be a request, one of these request interfaces, and then the response. And so we can call this function and say, hello, whatever we want, and then it's going to return a classic greeting to us. Meanwhile, in the CDK folder, we have our Lambda function being bundled up. And every time we deploy the stack, we're just going to take the latest code that we've been working on, send it over to Lambda, and then we can invoke it. The second thing that's happening in the starter kit is a DSQL cluster. And this cluster, you'll see, it just kind of follows what you saw in the UI, right? So we have deletion protection, we have our tags, and if you're using TypeScript, you can get this like nice auto-completion to say, what else can I configure here? Now, I've gone ahead and created one of these already, and when you run it, this is what you get. You're going to get two outputs. These outputs are defined here at the bottom of the CDK stack that say what our cluster endpoint is and what the security, the IAM role for our function is. DSQL clusters have their own endpoint. Actually, behind the scenes is a big shared endpoint, which is really important because that's going to be part of how we provide automatic capacity management. But we present a unique endpoint to your cluster. This is just basically a UUID for your cluster, which makes it just really easy to connect in with Postgres clients because they expect a host name, right? So that's why we do it like this. And what I want to show you quickly is what it looks like to invoke our Lambda function. So here we say AWS Lambda invoke with the CLI. Here's our function name. And we're going to pass in name equals reinvent and write the response to that file. And then we can take a look at that file. Hello, reinvent. OK, great. What I want to do now is just show you what it looks like to connect. So we need to export a couple of variables to make the Postgres shell work. The first one is the PG user. I'm going to set that to admin. The next one is the PG database, which is going to be Postgres. Then we have PG host. And if we try and connect now, we're going to get a prompt for a password, right? So where does my password come from? And I'm going to get one from the AWS command line tool. That's my password. Feel free to copy it down because you'll notice that it's expired already. So the way this works is through a technique that looks a lot like S3 pre-signed URLs, if you're familiar with those. So the AWS SDK, what it usually is doing is making HTTP requests to a service saying, hey, I would like to download this file from my S3 bucket. And it's building an HTTP request that has headers, that has a body, and then the SDK is going to go and sign that request, right? So it's going to go and run these cryptographic hash functions over your headers and over the request body, and it's going to put a signature, right? And that signature is going to give us a tamper-proof property, so that if anybody intercepted your request, they can't modify it. And it's also going to give us expiry, and so if somebody managed to intercept this request, they would have a time-bound window in which to exploit it. And usually you can't do that because your request is being sent over a TLS connection. Something like S3 pre-signed URLs works a little bit differently because what you're saying is I, who have access to my S3 bucket, I'm going to make this request, but before I send the request, I'm just going to take that signed URL, and then I'm going to intentionally give it to somebody else, right? That's pretty much what's going on here. You'll see that this looks like a URL. Here's the host. It's our cluster. We have an action called db connect admin, and then we have that signature. And this is going to take the place of our password. So rather than giving a very, very short-lived password, I can just export this into an environment variable. And now we should be in. Oops. Did I get the host wrong? I remember what I didn't do. I haven't had coffee this morning. Demo.
Did you set the region?
Okay, there we're in. So I'm using a demo account, and I forgot to switch the profile of the shell. But we're in now, and we can just run kind of standard Postgres commands. And what I'm going to do is exactly the same thing in our Lambda function. So we're going to go over to this Lambda function, and you'll notice that there's a file here called db.ts. And this is essentially the Node Postgres driver. I've just gone to their README, and I've copy-pasted everything into this file. There's one change, which is this password. And so the password is going to come from calling a function, and that function is essentially the same thing that we just did on the command line, right? This is, hey, use the SDK to generate one of these tokens. And you'll notice that the cluster endpoint is coming in through an environment variable. So let's just wire this up quickly. We're going to say my cluster endpoint.
And while you do that, we do take questions. So wave your hand if you want me to grab the mic and get a question. Yeah, we have a question. How about that? All right.
Thank you. You mentioned that you don't need security groups and things like that. Does that mean DSQL runs as just like a general service, kind of like an S3? You don't have it in your VPC or something like that?
So we do have public endpoints, and we do have the option to set up a VPC endpoint if you need that. But it would be through a VPC endpoint, yes, correctly. Another question.
Is there a MySQL flavor of DSQL? No?
Not yet.
Not yet? Okay.
But we are very, not very specific in terms of SQL dialect. So if you have an application that's pretty much sticking to the general dialect, you should be able to use DSQL as well. Okay, one question.
Just to touch on the VPC endpoint part, I noticed sometimes in some newer services in AWS, even if you do have VPC endpoints, you don't necessarily always support endpoint policies. Do you support endpoint policies for DSQL?
We just added resource-based policies, yes.
Okay.
Yeah.
That's really important for our...
What's the use case? Is it?
We don't want potential of... We don't want the potential of, people getting access to our VPC, or security requires it on our side. I can't remember the exact details, but there's always a sticking point for us.
Got it. Thank you.
Yeah, we've actually got a really detailed blog post on how to do this. If you want to chat to me afterwards, then I can give you the link. But it goes through, there are 5 different ways that you can lock this down. And as Raluca just mentioned, and you saw on the cluster creation page, is that advanced tick box you can put in. You can put in just any kind of standard AWS policy language stuff there. So you can say, restrict to these IP addresses, restrict to these VPCs, anything like that. Okay, I need to quickly update you on what I did in this. So we've changed our Lambda function to say, give me one of these pools, database pools, and we're going to run a query. And so the idea is that if we're still able to see our greeting, then we've connected to DSQL, right? And I want to quickly draw your attention to this function here. This is going to make sure that we're going to reuse our connections between Lambda invocations, right? So the first time our Lambda starts up, we're going to have to initialize the pool. This pool is going to maintain 20 connections, up to 20 connections in the background. Like our Lambda function is going to get one request at a time, so this is totally overkill. But you can do kind of whatever you want to do here. But every time a connection's opened, we're going to go grab one of these authentication tokens. Now, this is just a really, really fast operation. It takes something like 20 nanoseconds to run. And if you're using a service like S3 or Dynamo, you're actually running this all the time on every request. With DSQL, you're just running this code once per connection. OK, the second thing we've done here is we've just asked the SDK to wire in our endpoint into the Lambda function. And then down here, we've told the IAM that we want to allow this Lambda function to connect to the database. And if I do that and run my function, I'm expecting it to fail. And the reason I'm expecting it to fail is because we've not yet told the database to allow our function in, right? So we've told Lambda, hey, the role that you have is allowed to connect to this DSQL cluster, but the DSQL cluster is trying to see whether our application, which is connecting in as a user called my app, is allowed to connect. And we haven't actually set that up yet. So let's do that quickly. We can do create role my app with login. And then I got to do some copy pasting of this ARN to say that this AWS ARN is allowed to be allowed permission to grant this to use this role. And if we try run that again, we should hopefully see success. OK. So the way this works, we can actually just take a look at this table quickly. You don't have to remember these names. I just used tab completion there. So there's a namespace in the database called sys that contains all our metadata. And you'll see that we've got a mapping that says, this IAM role is allowed to become this Postgres role. And the reason we went this direction in the DSQL design is that it exposes the full power of Postgres permissions, right? So if you want to say, here's a role that can only read these tables in the schema, or a role that has read-write or only to specific tables, you can do all of that with the standard Postgres role system. The only thing you need to do is sort of bind which IAM entities are allowed to become which roles. OK, so I'm going to get coding on our banking application. But before we do that, I want to quickly show you what the schema looks like. So we're going to have a table called accounts. And accounts have an ID. That's just an integer, and it's a primary key. And they're going to have a balance, which is an integer too. And once we have this set up, we can start to do a balance transfer, right? So we can run a transaction where we have some money in one account, some money in another account, and then we can move it over. So I'm going to do that the wrong way, and then we're going to talk about why that's wrong.
OK. Can I start talking about transactions? You might not make it to the next session, but as a database geek, I really love transactions. And the reason I prefer to do database changes inside the transaction is because it allows me to specify all the changes to succeed or fail at once. So you're familiar, everything that goes between a begin and then a commit or a rollback will succeed together or fail together. So that's the atomicity of a transaction. Do you want to?
Yeah, so I just did it the wrong way, right? Because what happens if after running this statement, my laptop died, right? At this point, what I'm intending to do is move some money between accounts, but any number of things that can go wrong, right? We may lose connectivity, database may crash, but there also could be business logic errors, like maybe I don't have enough money, right? What happens if I only have $10 to my name and unfortunately, I get into a little bit of debt, and so I'm trying to pay off all my debt at once. So I'm going to go to Raluca, I'm going to go to somebody else, I'm going to say, started transaction, how much money is in my account? $10. Let's go and pay both debts off at the same time, right? And so without any kind of consistency checks, 2 transactions could start. They could both determine that I have enough money to pay. We could deduct money from both accounts, and then we're going to land up with a bad outcome where I've sort of been able to spend $20 despite only having 1. And so for these kinds of reasons, we want to make sure that we're always using transactions. DSQL supports something that's very equivalent to Postgres' repeatable read isolation, except it's just one notch stronger than that. It's a strong snapshot isolation mode. And for those of you who aren't deeply familiar with isolation modes, really the easiest way to understand them is through this concept of anomalies. And an anomaly is something that you can see in your transaction that doesn't make sense, right? So like a good example of this, one you've probably all run into, is a phantom row, where you run a select statement, you don't see a row, you run a select statement again, you see the row, you run it again, you don't see the row, right? These kinds of things are happening because there's multiple transactions running on the database the whole time. And so the job of the database is to try and isolate our transaction as much as possible to give us the illusion that we're the only user on the system, because that's going to allow us to write correct code. And because DSQL is slightly stronger than repeatable read, that means that there are fewer anomalies. In fact, DSQL only has one anomaly called write skew. And so if anybody would like to talk about write skew later in this talk, depending on how much time we have, we can do that.
Yep.
Okay, so what I want to do right now is start to take this Lambda function that we have and turn it into a little banking application.
I'm just going to add one thing to what Mark just mentioned. Strong snapshot isolation in DSQL means we have this property of being strongly consistent. So whatever you write will be immediately seen by all the other places you read from. So you don't have to worry about routing your query to a specific reader or to a specific endpoint, because wherever you read from, you're going to immediately see what has been written, and that is strong consistency as opposed to eventual consistency, which some other database flavors would offer. So that's strong snapshot isolation. And then there's 2 more things. We call transactions ACID because they're atomic, consistent, isolated, and durable. And I'm going to quickly touch on consistency while Mark is doing all the coding there. That means you don't get these phantom money transfer where you've sent, you see the money in one account, you don't see it in the other. Everything stays consistent. The database moves from one valid state to another in a consistent mode. And then you have durability, which means the database will recover in case of errors for you. So once you've acknowledged that a write has been made to the database, you'll always continue to see that data persisted in the database. You don't have to worry about machine restarts or failures. All right, let's see. What are we doing?
I am doing ceremony. So this is kind of a little boring code, but I wanted to, if we have time later on in this talk, we can maybe move to like a bit of a higher level of abstraction through an ORM. But I wanted to take the time to show you what it looks like to write these transactions at a very low level. So we sort of have a try-catch pattern, and then within the try-catch, we have a begin and commit, right? And that's going to start our transaction boundary. And then if anything goes wrong, we are just going to throw the error. And we're going to have to take care to return this connection to the pool, right? Otherwise, when we run the function again, we're going to start to go from 20 available connections to 19 until we eventually have an outage. Here's our pay state. Here's our pay query. So we're going to be taking money out of the account. And notice how I'm using bind variables just to make sure that we don't have a case of Bobby drop tables going on here. And this is the payee. He's going to be receiving money. And we need to do a little bit of checks here. So what can go wrong? Think about that for a moment.
Let me know if you need me to hand the mic to anyone. Okay.
So the thing is, let's say we are running two transactions, same transactions.
Yep.
We're drawing the amount from the bank account.
Okay.
The bank account has $100 balance. The transaction is also doing the same, like it's withdrawing $100 because both the transactions running in parallel. How are you going to handle that situation?
That's an excellent question, thank you. Because it segues into what I wanted to talk to you next about, which is how DSQL handles concurrency control. So we do optimistic concurrency control, which means when two transactions try to update the same row, they will both be allowed to try, and then the first transaction to issue the commit will win, and the second transaction will have to retry, and that retry logic needs to be embedded in the application code. And so the ideal design pattern is idempotent, so that transactions can just retry on failure, they don't need to check embed any business logic. So that's optimistic concurrency control. And if you were to use the opposite, which is pessimistic concurrency control, this used to be my nightmare as an Oracle DBA. So you'd get all these sessions or the transactions lining up, waiting for a row lock. I think it was called, the wait event was in queue transaction row lock contention, something like that. And in Postgres, it will be a lock relation. So what happens there is the first transaction trying to update a row, grabs a lock on that row, and then the subsequent ones will just line up and say, I want to update that row, I want to update that row. And eventually, either the first session needs to be killed or it just finishes doing the processing it needed to do, and then the whole thing unblocks. And that particular scenario also requires an abort and retry logic, except in DSQL, you just get notified sooner, and you need to retry. Okay.
So the transaction that's fine. So the transaction, the first transaction, basically, when it acquires a lock on the row,
Yeah.
the row will be released only when
There's
the
no
commit
lock.
happens?
In DSQL? Pardon? Mark, your variables are all
They are?
wrong. Thank you.
Thank you so much. You probably just saved us an hour.
So the release is not going to happen.
There's no lock. It's lock-free. There is no lock in DSQL.
Okay.
So that's why we can also support higher transaction throughput, because you don't have to wait for another transaction. There's no coordination there. Everybody who wants to update will just issue the update, and then the first one to have the commit wins, and then the other ones get serialization error. It's Postgres error code 40001. Oh, and by the way, I have to tell you this. If you go to the AWS booth in the expo, in the Venetian, and they ask you the one unique thing you've learned from this session, and you tell them about serialization error 40001, they will hand you a hoodie, an AWS hoodie, and a sticker, a DSQL sticker. Do you have more questions? I have one more. Thank you.
Yeah, we're actually gonna go look right at conflicts in a moment, because as soon as we start to run this a bunch of times, we're gonna see exactly your question in action. So let's see if we can invoke this.
Mark, I have one more question. Can I take it?
Oh yeah, let's take that.
It's actually not a question, a little bit of a contrarian comment, if I may.
Okay.
And don't get me wrong, I love the SQL, and I think it's a marvel of engineering and brings a lot of value. I was just want to say that I'm not totally sold on that the optimistic locking approach used here is straight away better than classical Postgres, because having to do idempotency puts a burden on the developer that if you run on repeatable read committed mode, which is the usual for Postgres, and most applications are fine with that. Right. It's an extra burden, adds friction on the application developer side, and having to have retries can also, at point, also hamper performance, because you're doing retries versus just waiting a little bit for a lock to be acquired. So just this comment is not, it's something that makes sense, and it's an acceptable compromise, but still a compromise. I don't think it's just straight out better.
We call it a trade-off. It is what you need to obtain a higher throughput, right?
So we're going to actually dig into OCC in a minute. So your 2 points, I think there's, is it better than Postgres? Is it ergonomic? And what about performance? Let's make sure we cover all three of those. So our function works. We're returning the balance using the Postgres returning syntax. And so if we run a bunch of times, we can see our money going down. So I'm going to quickly run this setup script, and then we can, we have 1,000 accounts, and then we can do, let's see if I remember where we are now. We want to have chat 2? I think so, maybe. Okay, so this is going to open up to 1,000 requests in parallel, and it's going to call that function. And every time it calls that function, it's going to say, pick a random account, a random payer, a random payee, move some money around, and then this is going to keep track of the errors we get back. And you'll see that we're getting change conflicts with another transaction, right? And so the reason this is important from a correctness point of view is that we are running all of these checks here, like does the payer exist, does the payee exist, do I have enough money? And because we have this concurrency going on, DSQL is detecting, and it's detecting here on line 43, that somebody else is mucked with the data that you've been working with, right? And so you need to try again. And the way we do that is we're going to handle this error code and just try again. So we'll say while true, and then I need to indent everything. And then in our catch block, this gets a little funky in TypeScript because of error handling. But what we're going to say is if the error is not a PG error, something else has just gone wrong, then we're going to run this old code. Otherwise, we're going to take a look at the error code. So this function here just lets us like get some type information out of the error. We can just run continue. And then we'll have a to-do over here. Now, it's kind of important, I've made this bug a bunch of times, to make sure that we are grabbing a new connection out of the pool inside this loop over here. Okay, and I'm going to do a little bit more decoration here, just so we can keep track of our retries. So we'll say retries is a number. That's a typo. And we'll say duration is a number 2. And then at the start here, we'll take the current time. And then down here, we will return the duration. We're going to do that down here too for a reason that will become apparent. Okay, and then we need to return retries too, right?
Right, so we just have some telemetry around the OCC retries, to your point. You can exactly quantify what your hotspots are, how many times you have to retry, if the application tends to have these hot deadlocks, and so on. So, if you do want, for example, not to have all the sessions retry at once, then you would add some exponential backoff and retries and things like that. But in this case, I don't think that's going to be required in the simple application. Hold on. I want everybody to hear what you say. Just hold on.
Just if I may. Absolutely. I like the word that it's a trade-off. That's exactly what it is. That's why I just want to make sure that it's not presented as a best solution. Because, again, if I run, for example, read committed mode using regular Postgres, I will not need to do this while true loop and check for the errors and handle the retries. I'm not saying this is better or worse. It's, again, a trade-off. But here you're forced versus not being forced, and therefore it's a compromise. Yeah.
Thanks. Does anybody have any other questions? Okay.
Okay, so this code is actually still wrong. And the reason is we need to handle our errors a little bit better over here. But we'll see what happens when we run it. So adding this retry loop is work, for sure. I've gone a little bit above and beyond in terms of adding telemetry because I want you to see when we run this code what the error rate is, right? And it's going to be really bad, right? And the reason it's really bad is that we only have 1,000 accounts, right? We're running at 1,000 requests per second. And so the chance of there being 2 concurrent requests to the conflict is going to be pretty high. Timeout exceeded. I think I'm leaking connection somewhere. Okay, give me a moment to debug.
I'm happy to take more questions in the meantime. I saw that hand first. I'll go there first.
Thank you. Yeah, I was just wondering what the problem was with, like you mentioned, you had to push the client acquisition inside the like retry loop. What's the issue you run into if you don't do that?
Yeah, that's a great question. Give me a sec. I can't do 2 things at once. Okay, so the reason we had a leak here is that I wasn't returning the connection to the pool. The reason we want to do that is, depending on how much time we get here today, I want to show you just how you can recover from other kinds of errors in DSQL, right? For example, when you're running on a single node system, what happens if your primary fails, right? Like you have to learn about the new primary, you have to shift your connections open. And so in DSQL, because we're a distributed system, each of your connections is actually running on a different machine somewhere. And so when something goes wrong, you're going to lose just a fraction of your healthy connections, depending on like what failed. And so it's really important that your application can take advantage of that and grab a new connection and keep going. And so the simplest way to do that is to simply grab a connection out of the pool when you retry, right? Because if anything goes wrong, and then you can change that catch handler to simply say, hey, if any of these conditions happen, just grab a new connection and try again.
We had one more question here. Yeah. And then I'll come there.
Do we have to pay for each connection? So if I open 1,000 connection, do I have to pay something if I don't run any query?
No. So the question is, how do you pay for connections? The answer is connections are free with an asterisk. And the asterisk is that opening a connection does a small number of reads because it has to do things like check your permissions, right? But the thing you're actually paying for is usage. So you're paying for reads and writes. And so once you've opened a connection, like you can just leave it there idle. It's fine.
Okay.
Okay, so we're done with that, and we'll notice that our min execution times are pretty low, but our max execution times are pretty high. And the reason for that is we're doing a bunch of retries. Okay.
I have one more question.
So what I'm going to do now is actually load this system up a little bit more. And what this script is going to do is just dump in 1 million accounts. And while we do that, we're going to quickly add another table, which is our transaction log table.
Mark, I have one more question.
Yeah.
Okay. Yeah.
Hey, I know when the DSQL launched, there was a few unsupported features like foreign keys, partition sequences. Are things like that planned to be added in the future, or is it like the distributed nature kind of makes it so they'd be not able to be implemented? Did I phrase that correctly?
Yeah, so foreign keys are on the roadmap. We do plan to be closing that gap with the Postgres compatibility. One more question here. Did you have one more question, or I missed? Oh, sorry.
So in a distributed database kind of thing, how do you manage, because you mentioned that write consistencies are maintained in optimized way, and once you get a confirmation about a write commit, it will be read across the cluster in the same way. But if somebody reads a transaction which is written in somewhere else, does the session needs to wait? How does it get the committed block from the storage? Because storage is being shared, not the data. So how does that happen?
Yeah, so this is the reason that we do optimistic concurrency control in the system, right? Because there's really two ways to do it. With pessimistic concurrency control, as soon as you do anything in the system, you have to go and sort of like put a lock there, saying like, hey, I'm busy here, right? And that would require us pushing down that locking information somewhere, right? With optimistic concurrency control, we don't do that. We just do our work completely independent of everybody else. And then when we commit, the commit's written to a single place, and that single place looks at everything that you're doing, and it checks if it's been, if somebody else has done something that interferes with it.
So you need to check, right? If somebody else made a transaction on the block that somebody else is interested in.
Right. And so it looks at the changes that you're making, right? So in this case, because both transactions are reading and writing the payer and the payee ID, so if we have one transaction that is 1 to 3, right? So it's account 1 and account 3, and the other one is account 3 and account 5, then because both of them have 3 in their write set, when they get to the point of commit, that's when the system called the adjudicator is going to look at that and say only one of these can go through, and the other one has to retry. And so there's like there's nothing happening at the storage layer to do this. It's all happening at the commit layer.
Okay. So do you have a memory share concept between the cluster also?
Everything is just fully independent.
Okay.
Yeah. Okay, so we have a table of transactions now, and all this is a record of everything we've done in the system. And there's 2 columns that are being automatically generated by the database. The first one is the ID, which is a UUID. And the reason we want to use a UUID here is for the same reason that you would want to use one in DynamoDB, right? That's going to just give you the best possible fan out, which is maybe a different philosophy than you would have on an instance-based Postgres system where you want to do everything sequentially to get the best I/O, right? In DSQL, it's just way better to go wide. And then the last column created out is just a timestamp. And so what we're going to do in our function is just populate this table. See if I get this wrong again. The payer first. Okay.
Did you assign the role to?
Did I do that?
I don't.
Maybe.
I missed it. Okay, good.
Thank you for checking me. Okay, so what I want to show you now is this table is going to start to fill up rapidly, right, when we start to run at scale. And we're going to want to be able to query that. So imagine this is a real application. Our customers going to our page, and they're clicking on their home page, and they want to see what transactions that they've run. And so we're going to want to run a query, select star from transactions, where we can pick out for this account, select star from transactions where payee ID equals that number, and then we see our log, right? And if we run this a few more times, we should see more rows. There we go. Okay, the RNG was on my side. But I want to show you quickly how to think about performance here. So if we do explain select from account, you'll see that we're doing a full scan on this table, right? Because there aren't any indexes. And what we can do here is, I'm actually going to use explain analyze, which is going to give us a little bit more information because this actually runs a query. So we can say create index. I'm intentionally getting this wrong for a moment. On transactions, payer ID, on transactions, payer ID, and I'm going to put created at in here for a reason. And we get an error, unsupported mode. And you'll see that we have to use this syntax called create index async. And the reason we do this in DSQL is because in Postgres, when you create an index by default, you're going to be taking a lock on the table, so nobody else can record any transactions, because the system needs to go row by row and make sure that it's building the index correctly. Now, Postgres has an alternative syntax called create index concurrently that does less locking, but it still does some locking because it has to wait for this sort of quiescent phase before it can start. And it also has to scan the table twice, which can be very expensive and cause performance impact. There's another small issue with create index concurrently, which is that there's no way to track it, right? And so when we were thinking about building the system, we wanted to solve all these problems. And create index async gives you a job ID that you can wait for. So if we do call sys.wait for job and put this ID in here, it should say it succeeded. And you can actually take a look at all of the jobs that the system has been running by digging into this table. And you'll notice that there's this index build that we just did here, but there's also these analyze jobs, right? Because the system is constantly looking at stats in your tables to make sure that, that it's building the right query plans. But if we go and run our query again, you'll notice that it's still doing a full scan, right? And this is just a little gotcha for you to keep in mind. Actually, I probably picked the wrong field here. Okay, we're using our index here. But if we picked a different ID, maybe one with fewer transactions, or if we had a smaller table, you may still see a full scan because the query planner is actually free to choose, right? It can say, hey, should I scan this whole table? If there's only 10 rows in it, then it might just scan the whole table. Or it's going to take a look at those analyzed jobs that are running. It's going to take a look at the indexes that are running and pick an efficient query plan for you. This may look very intimidating. If you're not used to reading query plans, just dump it in your favorite AI tool and it will do like a really good job telling you what's going on here. But I want to quickly call out a couple of things here. This is using an index and there is no sorting. And if we do something like order by created at descending, you'll see that there's still no sorting, just your eyes scan for memory, quick sort, anything like that, not in that list, because we actually put the timestamp in the index, right? So this is going to allow like the database to traverse the data in the right order. And what's really cool about create index async is you can do this fully online at any scale you want, and there's never any blocking, and there's never going to be any performance impact because it's built completely asynchronously in the background using dedicated resources for your index. Now, with that said, I want to show you how we can scale this application out. So this could get a little messy because, demo gods. So let's take a run. So this tool is a sustained load generator, and we're going to tell it how many accounts there are in the system. There's 1 million. And then we're going to give each host a target number of transactions per second. And what they're going to do is you'll notice this little in-flight counter over here. They're going to continue to open batches of connections until this number on the bottom left gets to their target. And so with this running, we have 4 machines driving 4,000 TPS. And if we jump over here, we can do And this is actually going to go row by row and count every transaction we have. And if I do this again, it's going to be even slower. It's going to go row by row of even more data, but this number should start ticking up. Now, that didn't fail, so let's go a little bit higher. At this number, I should hit the account quota for Lambda, right, on my system. But pay attention to these numbers here, error and OCC. We're not getting any errors, and we're not getting any OCC errors. And the reason for that is by sort of cheating with the number of accounts, right, we've created more write keys. And so the probability of any of these transactions conflicting is low. Now, this is obviously a little contrived example. I didn't want to spend too much of this talk getting into like some kind of like really complex real-world schema. But the takeaway for you is to think about designing your app and schema so that you don't have what we call hot for write keys, right? Okay, while that runs, let's take a quick look at pricing. If we jump on over to our cluster,
Can I just grab everyone's attention to highlight that we went from 1,000 concurrency to, what was it, 10,000? How much did you put in the system?
yeah, we're running at about 10,000 TPS right now.
And we didn't need to provision higher instances or more parameter groups with a higher number of connections allowed or any of that. So that's another nice thing to bear in mind.
Yeah. Nothing to patch, nothing to scale. Just send traffic at the system, it scales for you. And if you're using something like Lambda that can scale, then you also don't have to worry about the compute. So this is the, so we're on the cluster page. I've clicked on metrics, I clicked on usage. And you'll see that there are, there's really two metrics for you to track. There is total DPU. A DPU is a distributed processing unit, and this is like a pay-per-use metric. If you use to DynamoDB, in DynamoDB you pay for writes, and you pay for reads, and you pay for storage. And DSQL has all three of these units too, but it also has an additional one, which is called compute. And this is like Lambda, you're paying for compute seconds, because we're a SQL engine, right? And so you can run these complex queries that are doing joins, that can be doing aggregates, you can do Fibonacci in it, and so there needs to be some way to track that usage. DPUs are, you can monitor them with CloudWatch. I've also built a little tool where if we can take this cluster ID, make sure I'm in the right place. We can paste it in here. And that's going to go fetch those CloudWatch metrics, just sum up all of the data points, run it through our pricing calculator, and you'll see that we spent $2 on DSQL. If I stop this load and we wait a few minutes and we run this again, it will still be $2, right? If we wait 5 minutes and leave the load running, it will eventually tick up to $3 or $4. I've run this workload for 20, 30 minutes, and I came back, and it's running at 1 million TPS, and I spent $10. So this is one of the really cool things about DSQL is that not only are you not having to provision hardware, but the database just out of the box is going to give you this ability to scale up and pay only for what you're using in that moment, right? So if this load stops, that's it, you're done. Frozen in time, the thing that you're going to continue to pay for is storage. Okay, I think we have 5 minutes left, so we should probably wrap it up and take any final question.
I have a 10-second comment, and then the rest of questions, if there are more, we
I'll be hanging around outside afterwards.
Thanks, everyone. Please remember to fill in the survey for the session.